Nuclear fission is one of the most powerful reactions humans have learned to use. At its simplest, it happens when the nucleus of an atom splits into two or more smaller nuclei. But that simple description hides the scale of what is happening. The nucleus is the dense center of the atom, where nearly all its mass is packed into an incredibly tiny space. When a heavy nucleus breaks apart, the process can release gamma radiation, fast-moving fragments, and extra neutrons. Most importantly, it releases energy far beyond the scale of ordinary chemistry. Burning fuel rearranges atoms through their electrons. Fission changes the nucleus itself. That is why a small amount of nuclear fuel can produce a huge amount of heat, enough to power cities or, if uncontrolled, create devastating explosive force. The reason heavy atoms can split is tied to the forces inside the nucleus. Protons push away from each other because they all carry positive electric charge. At the same time, the strong nuclear force pulls protons and neutrons together, but only across extremely short distances. In small and medium nuclei, that balance can be stable. In very heavy nuclei, such as uranium, the nucleus is large enough that the balance becomes easier to disturb. If a neutron enters the nucleus, it can add energy and make the nucleus stretch and wobble. Physicists often compare this to a liquid drop deforming. If the nucleus stretches past the fission barrier, it cannot pull itself back together. It divides into smaller fragments, and those fragments fly apart at enormous speed. Fission releases energy because the products of the split are more tightly bound than the original heavy nucleus. Nuclear binding energy is the energy associated with holding protons and neutrons together. Some nuclei are held together more efficiently than others. For very heavy atoms, breaking into medium-sized nuclei can produce a final arrangement with greater total binding energy. The difference is released, mostly as kinetic energy, meaning the fragments move extremely fast. When those fragments collide with nearby atoms, their motion turns into heat. That heat is what nuclear power plants capture. The principle is related to fusion, but the direction is opposite. Fusion releases energy by combining light nuclei. Fission releases energy by splitting heavy ones. Both work because nuclear structure stores vast amounts of energy. The discovery of fission came at the end of 1938 and changed physics almost immediately. Chemists Otto Hahn and Fritz Strassmann found evidence that uranium, after being bombarded with neutrons, had produced much lighter elements. That result was difficult to explain by ordinary nuclear reactions. Lise Meitner and Otto Robert Frisch soon recognized what had happened: the uranium nucleus had split. Frisch named the process fission, borrowing the term from biological cell division. The discovery became even more important when scientists realized that fission released additional neutrons. That meant one split nucleus might create the conditions for more nuclei to split. A single event could become many events. In other words, fission was not just a reaction. It could become a self-sustaining chain reaction. A chain reaction is the heart of nuclear fission technology. Imagine one neutron striking a fissile nucleus, such as uranium-235. The nucleus splits, releases energy, and sends out more neutrons. Some of those neutrons may strike other uranium nuclei, causing them to split as well. If each fission event leads, on average, to one more fission event, the reaction continues steadily. If too many neutrons escape or are absorbed without causing fission, the reaction fades. If each event causes more than one further event, the reaction grows rapidly. This multiplication is what makes fission so powerful. Engineers do not simply care about the fuel. They care about how neutrons move, slow down, escape, and get absorbed. Controlling neutrons means controlling the entire reaction. Not all nuclear materials behave the same way. A fissile nuclide can split easily when it absorbs a slow, or thermal, neutron. Uranium-235 is the classic example. A fissionable nuclide can split too, but it may require a fast neutron with much higher energy. This distinction explains why many reactors use moderators. Neutrons born from fission usually move very fast. A moderator, such as water or graphite, slows them down through repeated collisions. Slower neutrons are more likely to trigger fission in certain fuels, making the chain reaction easier to sustain. Reactor design is therefore a careful balance of fuel type, moderator, geometry, coolant, and neutron-absorbing control systems. The goal is not simply to create fission. The goal is to keep it stable and useful. Most fission events do not split the nucleus into equal halves. They usually produce two charged fragments of comparable but different sizes, often with a mass ratio around 3:2. This is called binary fission, and it is the most common form. But fission is not perfectly predictable. A uranium nucleus can split into many possible pairs of daughter nuclei, creating a broad and somewhat chaotic range of products. Rarely, about a few times in every 1,000 events, fission produces 3 charged fragments instead of 2. This is called ternary fission. The smallest fragment in such an event can range from something as small as a proton to a much heavier nucleus. The important point is that fission is probabilistic. It produces patterns, but not identical products every time. Because fission changes one element into other elements, it is a form of nuclear transmutation. Uranium does not simply become smaller uranium. It becomes different atoms altogether, many of which are radioactive. These fission products often contain too many neutrons to be stable, so they decay over time, releasing radiation as they move toward more stable forms. This is one reason spent nuclear fuel is hazardous after use. It contains a complicated mixture of radioactive daughter products, each with its own half-life, radiation type, and decay path. Some isotopes decay quickly and produce strong short-term radiation and heat. Others last much longer. The waste problem is therefore not only about how much material exists, but about how dangerous it is, for how long, and how securely it can be managed. Fission can also happen naturally. In spontaneous fission, a very heavy nucleus splits without being struck by an outside neutron. This occurs in extremely heavy isotopes whose nuclei are already unstable enough to break apart on their own. Spontaneous fission was discovered in 1940 by researchers in Moscow, including Flyarov, Petrzak, and Kurchatov. In the broader universe, however, fission is not the main engine of creation. Stars are powered by fusion, and most elements essential for planets and life were formed through fusion and other astrophysical processes, not fission. Still, under rare conditions, nature can assemble something surprisingly reactor-like. Ancient natural nuclear reactors once formed where uranium deposits, water, and geometry allowed a self-sustaining fission reaction to occur without human design. The same chain reaction can be used in very different ways. In a nuclear reactor, the goal is controlled energy release. Control rods absorb excess neutrons, coolant removes heat, and the reactor is designed so the reaction stays near a steady level. The heat is used to boil water, produce steam, spin turbines, and generate electricity. In a nuclear weapon, the goal is the opposite, a superfast, uncontrolled release of energy before the material can blow itself apart. This dual use is why fission has always carried a heavy political and moral burden. The underlying physics is the same, but the engineering purpose is radically different. One system stretches the reaction into continuous heat production. The other compresses it into an instant. The energy density of fission is extraordinary. Fissioning a given amount of uranium-235 can release roughly 1,000,000 times more free energy than burning an equivalent amount of methane or using hydrogen in fuel cells. That comparison explains why nuclear power remains attractive despite its complexity. A small quantity of fuel can generate huge amounts of electricity with very low direct carbon emissions during operation. But high energy density also demands high responsibility. The system must handle intense heat, radiation, neutron flux, radioactive byproducts, and long-term safety. Nuclear power is not simply a bigger boiler. It is a technology where microscopic events inside atomic nuclei create macroscopic engineering challenges. The reward is immense energy. The price is precision, regulation, and careful containment. Waste is one of the hardest questions in fission. Fission products are radioactive, but spent fuel also contains materials created when neutrons are absorbed without causing fission. Uranium-238, for example, can eventually produce plutonium. Other reactions can create minor actinides, which may be more radiotoxic than many long-lived fission products. This is why nuclear waste debates often focus on fuel cycles. Reprocessing can recover usable material from spent fuel, extending uranium or thorium resources and reducing what is treated as waste. A closed fuel cycle aims to fission most actinides instead of leaving them behind. Thorium cycles can reduce plutonium and minor actinide production, though they introduce challenges such as strong gamma emitters from uranium-232 decay products. Every option involves trade-offs. Nuclear fission is a compact lesson in power, risk, and control. At the atomic level, it is a heavy nucleus splitting into smaller, more tightly bound fragments. At the engineering level, it is a problem of guiding neutrons, removing heat, and containing radiation. At the societal level, it raises questions about waste, weapons, energy security, and climate. The physics is elegant, but its consequences are not simple. Fission can provide steady electricity from tiny amounts of fuel, yet it can also create materials and technologies that demand strict oversight. That is why fission remains both promising and controversial. It shows that understanding nature at its smallest scales can give humanity enormous power, but only if that power is managed with discipline and responsibility. If you found this helpful, please like this video and subscribe for more explainers.